Today we start discussing section 3.38. In this section we will discuss rank of a matrix. First we have a few definitions. First we define submatrix. For an arbitrary matrix A of order m by n, we define submatrices for this matrix A. So the matrix obtained by deleting the rows of A or the columns of A or both, we can get so many matrices in this manner. These matrices are called submatrices of A. Now we have definition of square submatrix. If a submatrix is a square matrix, then it is called square submatrix. So if we get a square submatrix, we can define determinant of that matrix. So determinants of square submatrices are called the minors of the matrix A. Now these minors, if you consider a matrix, any an m by n matrix, if you have all the minors of order r plus 1 are 0, but if you get a non-zero minor of order r, that means there exists a non-zero r minor and all r plus 1 minors are 0, then you can define the rank of that matrix A is this number R. Now we have some remarks on these definitions. First we have a remark that introduces a notation row of A, that is the notation for rank of a matrix. In remark 2, if A is a null matrix, by null matrix we mean zero matrix, if all the entries are 0, then rank is 0 because every minor is 0. Of course, if A is not a null matrix or zero matrix, you can get at least one non-zero entry, then the rank never be 0. That rank is always greater than or equal to 1. If A is a non-singular matrix, that means determinant of that matrix is non-zero, then the order of A is the rank of A itself. That means the largest minor is non-zero minor is of order n. Obviously, the special case In, rank of In is n because In is a non-singular matrix of order n, and the rank of A is always less than or equal to minimum of m comma n, the number of rows and number of columns, because the largest possible square submatrix has order n. You cannot consider a square submatrix of order greater than n because that contains only n number of columns if n is less than or equal to m. Otherwise, the maximum possible order is m. So we can get the maximum possible order of a minor is minimum of these two numbers, m comma n. If A is a m by n matrix, we start an arbitrary matrix by a series of elementary operations, so row operations or column operations or both. It can be put into one of the following forms. That is IR, that is an identity matrix of order R, and all the other positions are 0, or IR 0 in row wise, and the other form is IR 0 in row wise, and IR itself. These forms are called any matrix A can be reduced to one of these forms. So this form is called a normal form of A. Now we have a remark. Using the normal form, we can define rank of a matrix A as R by looking into the normal form of A. In the other remark, we have an n by n matrix A. To find to find square matrices like P and Q, such that P is of order M and Q is of order N, both are square matrices, such that P into A into Q is the normal form. So we need to get two square matrices which transform this A to its normal form. So this is a interesting question, how to find this P and Q. Once you got this P and Q, you can easily write the normal form of this A. That's the idea of these P and Q. For this, we write method to find this P and Q. So first you write A is equal to IM, that is M by M identity matrix, into A into IN. Then reduce the matrix on the LHS, that is A, to normal form by performing elementary operations. You can perform row elementary operation or column elementary operations, or both. Then every elementary row transformation on A must be accompanied by the same transformation on the prefactor on RHS. That means IM. So once you perform a row operation on A on the left, then you perform the same elementary operation on IM, the first identity matrix. Every column transformation on A must be accompanied by the same elementary transformation on the post factor of RHS, that is the identity matrix of order N. Now we can see an example. Let me take A is equal to a simple matrix 1, 2, 3, 1, 2, 3. It contains only 2 rows. Then there are a number of sub matrices, a matrix of order 1, that is 1, 2, 1, 3, 1, 3, and so on. But the only possible sub-square matrices or square sub-matrices are these 6, 1, 2, 3, 1, 2, 1, 2, 1, 3, 1, 3, 2, 3, 2, 3. Determinant of all these 2 by 2 square submatrices are 0, while the minor of order 1 is non-zero. Then we define rank of A is 1. It is denoted by row of A is equal to 1. To find the normal form of this matrix A, we write A is equal to I. This first I is 2 by 2 and the last identity matrix is 3 by 3. Now you make the matrix in the LHS to its normal form. That is by performing row operations and column operations. First we perform R2 plus minus 1 times R1. Then this matrix will be 1, 2, 3, 0, 0, 0. The same row operation can be performed on the prefactor of A on the RHS. So that will give 1, 0, minus 1, 1. The rest of things are same. Now you perform two column operations simultaneously. So that will results 1, 0, 0, 0, 0, 0. That will be the matrix on the LHS. So we need to perform the same elementary operations on the post identity matrix of the RHS. So that will give 1, 0, 0, 0, 0, 0. That can be written as I1 0, 0, 0. So this is equal to so I1 0, 0, 0 is the representation of LHS. Then RHS is PAQ. So 1, 0, minus 1, 1 is the matrix P, and 1, 2, 3, 0, 1, 0, 0, 0, 0 is the matrix Q. So this is the way we find two matrices P and Q that help us to find the normal form of A. Now there are so many problems in the textbook. You need to work it out, and we will discuss doubts on the online discussion.